So we want to start off with the ideal gas law today, and the what we also call the equation of state. And if you think about it, if you have some gas in a sealed container, the pressure that the gas molecules exert on the walls of that container is going to be proportional to how many molecules you have in your container. It's going to be proportional to the temperature, because remember, the temperature tells us how fast those molecules are moving. And if they're moving faster, when they hit the walls of the container, they're going to hit it with more force, and you'll feel more pressure on the walls of the container. And it's going to be inversely proportional to the volume of the container, because the bigger the volume is, the more spread out the gas molecules are, and the less collisions they make with the walls of the container. So we put that all together, and we get the pressure times the volume is proportional to the number of moles times the temperature, and R is our proportionality constant. In chemistry, I think we use 0.0821 liter atmospheres per mole degree. In physics, we use 8.31 joules per mole Kelvin. And you have to be careful when you were using this, then your pressure needs to be in pascals, not atmospheres, and your volume needs to be in meters cubed, not liters. So just make sure your units work out correctly. But this is the constant we typically use in physics. You can also write it in terms of the number of molecules by using Avogadro's number and converting and using Boltzmann constant. But typically we'll use the other one. But this is equivalent. I'm not sure how I want to. Let's see, I had them do a worksheet, but I don't have it with me. Okay, we'll skip over the worksheet. Maybe you can edit that out later. So one of the tools we use is a PV diagram, where we plot pressure versus volume for a system as it goes from one state to another. What do I mean by a state? I mean that equation of state, PV equals nRT, the ideal gas law. A state is defined as pressure, a certain pressure, volume, temperature, and number of moles. So if we're going from one state to another, maybe from this location to this location, we can obviously get there in quite a few different ways. And one of the ways we can get there is by keeping the temperature constant. That's called an isothermal process, constant temperature process. And I've drawn some of them in here. And going from this point to this point, going from the first dot to the second one, the first state of the system to the second one, we could stay along a certain isotherm. We could keep the temperature constant if we followed that path as we changed the state of the system from one place to the other. We also could have followed a number of other paths. We could have kept the pressure constant until we got to this point, and then kept the volume constant and gotten there that way. So there are a number of different ways, and some of them are sort of easy to calculate, and we can, like the red line or the constant temperature line, there's special ones that we'll talk about. There are 4 special processes that we'll talk about. And what is our system? Our system typically, because we're talking about gas and it expanding and doing work, so typically we have a closed cylinder with a piston that can move with no friction up and down. And our gas is inside that piston. We can add heat or remove heat from the system. We can allow the gas to expand. The volume of the system can change, or we can do work on the gas and push the piston in. And this is not an abstract construct. This is something that, if you're familiar with the internal combustion engine in your car, this should be very familiar to you. The gas in that piston, there's a piston that looks just like this. And the gas ignites, gets hot, expands, does work, makes your car go, right? And then on the next cycle, that gas is pushed out, new gas comes in, and it ignites, heats up, expands, does some work, makes your car go. So we know about engines that work this way, and this is our very simple system, but also very applicable to our engines and cars and things like that. Okay, so let's put some of it together. Our equation of state, our ideal gas law, tells us that relationship, and we can look at certain particular cases. One of those is for a sealed system where the number of moles of gas does not change. So if N is fixed, if our piston doesn't leak, then the number of moles of gas is the same, so that doesn't change. R is already a constant, we know that. And if we're following along an isothermal process, then we know the temperature doesn't change. And so we can write PV as a constant for an isothermal process, or P times V at our initial location is going to equal P times V for our final location. So let's take a look at what that looks like. A constant pressure process on a PV diagram would look something like this, right? The pressure doesn't change. We're going from an initial state to a final state, or the other way, maybe this is our initial state and this is our final state. Either way, the pressure doesn't change, but the volume is changing. So that's what it would look like on a PV diagram. If the volume was constant, it would look like this, right? So that's making some sense to you. The volume doesn't change, but the pressure does. How would you go about achieving a constant pressure process? That's one that we often would like to do. And an example would be you have a piston that's free to move frictionlessly, and you put a weight on top of it. So if we draw a free body diagram for that piston, we have the weight down and the force of the gas pushing up. And what does that equal to? It's the pressure multiplied by the area of that piston. As our gas expands or contracts, the weight of the piston is not changing. So that means, and the area of the piston is not changing. So that means the pressure has to be constant. If the pressure wasn't the same, then the piston would begin to accelerate right in one direction or the other. But as long as we can move this in such a way that it's controlled and it's in equilibrium, then we know that those two are always equal to each other. So we could figure out if we were given the height at an initial temperature, and we want to know what the height would be at some final temperature, we could figure that out, right? We could use our equation of state, PV equals nRT, and the temperature over the volume is equal to a constant because the pressure is not changing, the number of moles is not changing, and R is our constant. So T1 over V1, our initial temperature and volume, would have to equal T2 over V2, our final temperature and volume. So we could go ahead and plug those numbers in. Now notice I'm using Kelvin temperature, and it's often confusing. Sometimes we use Celsius, sometimes we use Kelvin. You're always safe if you use Kelvin. Where we can substitute for Celsius were in equations where they use delta T instead of T. So if your equation has a delta T in it, then you can use either Kelvin or Celsius. If your equation has a T in it, you must use Kelvin. because delta T is a difference between two temperatures, and both of these scales have the same increment, so the delta T would be the same for either of those scales. So in this case, we can plug in our values, and the volume of a cylinder is the cross-sectional area times the height, and we can figure out what the final height is given the gas increase in temperature. And it makes sense now, right? We know something about gases. If we put some heat and we increase the temperature of the gas, right? We've gone from 273 to 318. If we've increased the temperature of the gas, those molecules are moving faster, they're pushing harder, the piston's going to go up, and it's going to go up until the gas pushes the same amount and the pressure is the same as it was initially, and the volume would have to be bigger for that to happen, because if the molecules are moving faster, they're going to hit that harder, so there have to be fewer collisions in the same amount of time. So the gas molecules have to cover a bigger volume. So think about through and see if your answers make sense. One of the things we've talked about is that temperature tells us how fast those molecules are moving, the kinetic energy, the average kinetic energy of the molecules. And yeah, you sort of took my word for that initially, but I want to show you that that's true. You can use, again, the fact that the pressure is the force over the unit area, and look at what's happening inside the container with the fact that those molecules are hitting the walls of the container and bouncing back. So you can look at some momentum conservation and use the equation of state, the ideal gas law, and work through some of the calculations. Your book does it for you. But what you get is the average kinetic energy is equal to 3/2 kT. The average kinetic energy is proportional to the temperature. And that's what I told you earlier, that temperature tells us the average kinetic energy of the molecules in the gas.